has some ratio to its radius. How do you formalize that? Well, you take an arc length integral. So how do you take an arc length integral? Well, you take the curve. You know what? Let's switch to blackboard. Probably going to be easier to explain. You take this curve, you split it up into differential line segments, and then for each of these, this gap is dx, and this gap is dy, hence the slope being dy dx. Well, this is unofficial. Technically, dy dx is not a ratio, but it helps with intuition. So what's the total length of this curve? Well, just use the Pythagorean theorem. It's a finite sum of, what's this? This is the square root of dy squared plus dx squared. So it's a finite sum of dy squared plus dx squared over all of the line segments. If you're feeling really funky, you can rewrite this as dy squared over dx squared plus 1 multiplied by dx. You factored out the dx. So this is for the finite sum, but of course, since the number of line segments approaches infinity, the finite sum, just like a Riemann sum, is going to get turned into an integral. So it's going to be the integral of the square root of 1 plus, this is just the derivative squared, dx over, well, whatever range you want to integrate over. So, how does that work for a circle? You take the defining equation of a circle, or at least of the upper half, which is implicitly x squared plus y squared equals 1. Then you can split it into two halves. The positive root and the negative root, which just gives you the lower half of the semicircle, the lower semicircle. And so, all you have to do is take the derivative of that. And what's the derivative of this? Well, it's just going to be d dx of 1 minus x squared to the 1/2. Which is, by the product rule and chain rule, you take the 1/2 out, you install the minus 1/2 here, and you multiply the rest by the derivative of whatever's inside, minus 2x. So you cancel these two out, and you get minus x over the square root of, well, this doesn't matter since we're squaring.